Consistency. I keep going. I want to talk, in my presentation, I basically want to talk about this equation, right? H of x and p is equal to 0. X is something that describes your like system, your gate, your initial conditions, all that stuff. It's typically a large vector, high dimensional. That 0 back here is also a vector, and the number of dimensions of x and 0 are the same. So we have the number of equations are equal to the number of x's that we have. And then I throw in p. Here p is a scalar. You could also think about extending this to more dimensions, but let's keep p as a scalar. And that basically means we have one more unknown, then we have equations, which means we get a continuum of solutions of this implicit equation. And that continuum of solution basically describes the relationship between x and p, and that's what we are interested in. And I want to give you a few examples of that equation in molecular motion in just a second, but before I want to do this, I want to give everyone who's not familiar with the math a bit of an intuitive understanding of what we're looking at. Right? And to that end, I really need to stretch your imagination for a bit. Yeah, I hope you bear with me. Imagine you're on a mountain. Okay? So maybe you took the cable car up, had lunch here, and then maybe walked up to the top. Just imagine. Your position on that mountain is given by a coordinate that I'm going to call x and the coordinate that I'm going to call p. And then at each point, that mountain has a height. It's called this elevation, x of p. And if I now want to assemble such a function h, I will do one small thing. I will take the elevation and subtract 1700 meters, right? I need a scalar, one-dimensional h, because my x also is one-dimensional. So what that gives me is the height above 1700 meter on that mountain. That's what this h is, that function h. And now when I go to the original form that I had on the previous slide, h of x and p is equal to 0, that basically tells me I'm looking for all the points on that mountain that have an elevation of 1700 meters. Right? And that solution is already on the map, right? That's that contour line that you see here. Here, let me highlight this, right? And that's the solution, right? It's a curve, in this case a closed curve, of all the points that have that elevation. And if you're interested in this relationship between p and x, you see that you will have a hard time formulating that as an explicit equation, like x of p. Like over here, for those p's, here there's no solution x. If we look here, there's actually 4 different solution x for the same value of p. So it's quite different, these implicit equations, than explicit equations. What you also see is that it doesn't really matter what is x and what is p. If I turn the whole thing 90 degrees, it will still somehow look the same. Right? So that's basically what we're talking about. Now, numerical continuation means are methods to compute these solutions, and they all have in common that they start at a known solution. And then there's different flavors. One of them is basically if you have a solution, compute the derivative. On a mountain, that means computing the gradient, which points straight up, and then you don't go there, right? You move in the null space of that derivative. On the mountain, that means perpendicular to your gradient, which gives you a nice tangent along that contour line. And you take a step in that direction. That's your prediction step. And of course, the step is straight, but the contour line curves, so I make a bit of an error there. But I have a good initial guess, and then I can do just the Newton-Raphson method correction to get me back on the contour line, and then you repeat that. And you keep doing that, and you walk around that mountain just on that contour line. So this algorithm is basically you walking on the mountain and gives you that curve. Now, this looks simple and clean, but there's actually some interesting things that can happen, right? Like all these contour lines, it looks like they're just closed curves around the mountain, and especially it looks like they're never intersecting. But if you remember, there was another mountain, oh sorry, you're just imagining this, right? In your imagination, there's another mountain right next to it, which has also contour lines running around. And then if you keep getting lower and lower and lower, at some point they have to touch. So if I look at a different function, h of 1290, so elevation minus 1290 meters, I actually get a point where these two lines intersect. This is a bifurcation point. And so when your algorithm goes there, you need to do some math to figure out that you just hit it by and then you can go in 3 different directions. So there's branches to this. In a mountain, this is called a saddle point, or typically a pass. They're always ugly because people build roads there. That's the they're typically ugly. Bifurcation points, where these lines, these solution lines, can intersect. So that's basically. Now, where does locomotion come in? And the first example that I want to talk about is not my own work, but work by Nelson Rosa and Kevin Lynch, who used this to find periodic solutions of a compass scale pole. So basically what they want is they want a periodic solution, so state at the beginning of one stride is equal to the state at the beginning of the next stride. And then they basically computed the state at the beginning of the next stride by integrating forward. Here, they're just integrating for a fixed time t, but you could also imagine you integrate until your foot hits a slope of a certain angle, gamma, and then you stop, and that's your next condition, and those two strides, or those two states, should be the same. I rearranged it, and bam, there's my equation, h of x and t. So that's the equation. Now, the second thing that I need is a starting point, right? And it turns out that just standing there is a good starting point for this because it's a perfectly periodic motion. So what you don't see here is that this biped shifts its weight from one foot to the other after every t seconds, but it doesn't move, so everything is periodic. And now they can do this continuation, and they get basically these contour lines which intersect at these bifurcation points, and by that they can create all types of different gaits, walking, branchiation on different slopes. So this is a weird slope. Depending if you're a walking person, this is a weirder slope. But you would call this branchiation. And so you can generate all these passive motions completely automatically from just standing still. Like what we did with this is similar, but with a simpler model that you have already seen like twice this week. Where we have a conservative model. So we removed all the losses, which means we can walk on level ground. And there we did the same thing, right? So what you see here is the same contour lines that I showed you on the map before, with the same bifurcation points and everything. And I think you've seen this in the past. Through this process, you can automatically generate all these different passive motion, and you find all the gaits that you see in nature, walking, skipping, running, you name it. It's all in there created completely passively. Here, my function h is a little bit curious, because I'm walking on level ground. I define the end of my stride by the foot hitting the ground. So there's no notion of time or slope in this. So h of x, wait, that's, and unknowns and equations, that should give me one solution, right? So what's going on here? Anyone want to guess?
It's non-linear.
It's non-linear, but that's so you could have multiple isolated solutions, but that's not the thing. Right? Why do I get branches? Why do I get solution
You've
mapping?
constrained it to be periodic, right?
Yeah.
Is that the restriction that?
No, that's the equation. Right? That tells me it should be periodic, and that should just give me one solution. So what's happening here?
You should have P. Where'd P go?
P is gone, because I walk on level ground. I always walk on level ground. I don't have time in there because I stop my stride when I hit the ground. I'm running out of my 15 minutes, you guys.
Are you starting at a bifurcation?
No, it has to do with energy, right? Because the system, as I said, it's energetically conservative. The intuitive way of thinking about it is basically if it's energetically conservative and all but one state is already periodic, that last state also has to be periodic. Because if it would be aperiodic, it would change the energy. So there's basically just n-1 equations in there, or in other words, these equations are independent. And you can turn this around. Like if I had a system that's not energetically conservative, and my first n-1 states are periodic, that last state can never be periodic, because if it were periodic, then energy would be conserved. And that's actually in an implementation an interesting problem, because numerical integration tends to have damping in there. So even though in theory stuff is energetically conservative, this time derivative of energy is never zero. So what we want to do here is we play a little numerical trick which is similar to adding a tiny slope. So I've mapped my dynamics with this value t, which is very, very small, multiplied with the gradient of energy. Why the gradient of energy? Because if I look at the time derivative of energy of this augmented dynamics, I get a quadratic term back here. So this is always positive. And then if I choose C to be positive, I can sort of, on average, add energy to the system, compensate for numerical damping losses. If I had to, I could also pick one that is negative. So it's almost like a tiny slope that helps me deal with these numerical issues. And it gives me back this form, right? I now have an h of x and c. And it's not nice for drawing these contour lines because c is always tiny, like 10 to the minus something. So every contour line looks like this, a straight line. And so you can massage this a bit more, add an additional equation where you constrain energy to be a certain value, and then you put all this together, throw c into your x vector, and you now have a much nicer form of this, where you get these wonderful bifurcation diagrams or contour plots that now correspond to different Hawking motions. So far, all of that was passive. But you can do very similar things also when you're interested in optimal motions, right? Optimal motions, I still want them to be periodic, so here's my periodicity conditions baked into this h of y. But now I also want to minimize some objective, save energy, and I'm talking about actuated systems, so my variable y, that's why I call it y, now has some description of the actuation in it as well. So everything got a little bit bigger, and you now have an optimization problem. If you phrase it that way, you realize that's not enough, because your optimizer will just tell you to put the robot in the corner and not touch it. Don't move. He will not use any energy.
So this is the best policy.
That's a global optimal policy. So we throw in an additional constraint that we call an operating point. So you have to move at a certain velocity or on a certain slope. Do something useful, and that something useful can be parameterized, like the speed that you want to move at. And now I have an optimization problem, not what I want, but if you remember, right, things are optimal if the first derivative is 0, so if I set up the KKT conditions for that, I can turn it into an implicit equation that has exactly that shape. So, great, right? I have my equation that I want. I need, for continuation methods, I also need a starting point. And this is where basically passive and optimal systems meet. We call this, passive is the new optimal. What do I mean by this, right? When I talk about passive systems, or I should say, yeah, I have no dissipation, or maybe I have dissipation compensation in the passive dynamic walker because it's walking downhill, but it's non-dissipative and non-actuated. And now I can get rid of the second thing, just, and then in my imagination I add actuators, so I shouldn't talk about passive systems, but loss-free systems, or loss-compensated systems. And with these systems I can do a lot of things, right? I can hop in place with all sorts of actuation trajectories. I have infinitely many possibilities. And all of these possibilities come with some cost, because I'm using my actuators. What can I also do? Well, nothing. I turn the actuators off, and because it's loss-free, I still get my passive motion, which I know is globally optimal because it has a cost of 0 because I'm not using my actuators. And for most of the cost function, it turns out that this optimality is actually a strict optimality. Right? The notable exception is mechanical work because the energy you put in has to be equal to the energy you put out. Right, so that's my starting point, and now the whole idea is basically take a passive solution and put it in this form, right? Use it as a starting point and then modify the parameter. So say my operating point is walking on a slope of a certain angle, and the passive walking on that angle, that's my starting point, has a cost of 0, and now I'll go ahead and slowly turn my slope as parameter p in this continuation process, and then I can go ahead and also change my speed, and then use this to generate basically families of gates that then span a space of optimal motion. So here in green you see the passive motions, and then in black this would be walking on all different types of slopes, and then here the yellow surface would be walking on level ground. And again, all of this can be generated completely automatically through these through this continuation methods. Here we manipulated the motion and the environment, but we could also manipulate the model. This is work that Max already showed a year ago, where the idea is basically, here's my lossy model, and I throw in a parameter that takes out the losses in a continuous fashion, so that when I set this parameter epsilon to 0, I have no losses. I can identify passive motion, which by definition is optimal, and then I do my continuation of these optimal solutions going back. And here you sort of slowly see this morphing process, and at every point of the process, the motion is completely optimal. That's how it looks like. Then you can put this all together, start with the algorithm to create all the passive motions, then pick one of them, change the model, moving over to the actuated version. And again, here's another video of the actuation slowly coming in and showing you how the motion changes as you go from loss-free to a lossy system. And I'll cut this short. Max already talked about indirect optimization, which is a way of doing these things, because you always have these good initial guesses due to the continuation process. There's papers, people who worked on this, in particular Nelson and Max recently. And that's my question, so thank you.
3 minutes for questions. Good.
So you're talking about starting with a loss-free system. If you want to do that with a real hardware, you'll be compensating friction and all these kind of other effects. Do you think you can tolerate small losses to a certain extent, so it's more realistically on physical system? Or you would have to be at like a really, really good compensation to get this working?
That's a good question. There's two answers. One, we do this in simulation, right? And in simulation, you can do everything. And then two is more like, how do you arrive at these lossless models, and do you really need them, right? Because the passive dynamic walker is not lossless, right? It's coming in, that's walking on a slope, which brings in energy. You could do this trick with Xc, so you can do some compensation, and then in the continuation try to drive that compensation down to 0. But I don't have the definite answer to that. So that's definitely something we've been thinking about, like how to generate these models. Andy?
Yeah, I'm just not understanding something, which is, I don't see what the lossless and optimal what the special thing you get is. We say we have a completely powered, completely not passive, I don't know, airplane or something, doing loops or whatever, but we have some way of generating solutions. You can still use these continuation methods, right? I mean, people use them.
You could.
People just take arbitrary differential equations and look for a limit cycle.
Yeah, but you would always need an initial guess. And then what I'm showing you here works completely without an initial guess. Or without a guess in the sense of real guess, right? All of this has been created in a structured way. So that's one part of the answer. The other part of the answer is, and this is not something I can prove, but I believe that these passive motions that you see here are somehow embedded in locomotion that we see in nature. So I think that's a good starting point, fundamental good starting point. Of course, I could use any other guess as well, but I think those may be good, but I can't prove it. And there's Art and then Aaron.
So there's no distinction between stable and unstable gates here.
No.
And so I'm wondering if you're using this as a starting point. So what if somebody wants to do control? How do you give them ideas on how to stabilize?
I don't know.
Okay, I have a second question. You said that if you take this map and you rotate it 90 degrees, everything would stay the same? I don't believe you. I need Sylvain and Robert to tilt the screen 90 degrees. Oh, okay, I get it.
And you're right. So this is interesting, and I glanced over this, but if I go to, these results here, you see that horizontal line. So this is a switching time and slope. And if you're moving periodically, they're basically interchangeable because I will always hit at the same time and I will always went down the same distance, so it's going to be a constant slope. But the reason why Nelson used switching time is because that way he could sort of move along that horizontal line, which is standing still, just moving your left leg from, I always call this the P gate, from left leg to right leg at different frequencies. And so that's the red line. All of them at the same slope. And I'm still trying to wrap my head around what's fundamentally going on, why this is easy when you use T as a parameter, and why it is hard if you use slope as a parameter, which is essentially this turning the screen 90 degrees.
You said something earlier in one of the other answers that you have to find an initial guess. Is it hard to find an initial guess? I mean, you have this correction step where you're starting at a point that's not a limit cycle and ending up on a limit cycle that's nearby. Can't you just start anywhere and just end up somewhere?
Yeah, so I'm not sure if I can answer this question in a fundamental fashion, because I mean, people obviously use optimization and there's similar approaches, and it works, right? And we have some intuition to use to find these initial guesses. For the indirect method, I think it's different because you not only need to find a state, which you sort of intuitively know how it should look like, but you also need to find a co-state. So I think there's some advantages here. So that's sort of the one part of the answer. The other part of the answer is that I'm also interested in these connections. Right? Like my long-term goal is to show that these passive oscillation modes is what we see in humans. And that process should allow me to show these connections. Now, the thing is that that route looks like around through a mountain. So when we try this, you go from passive to active. There's points where you just turn around and move back and then turn around again. And it's not a straight line. So that's still some open research. But that's also a motivation to do this. I think this can tell us something very fundamental about where certain emotions come from. Not that.
Do we have time for one?